Welcome everybody. Today we're going to talk about some rules for electric conductors. What I've drawn over here is just sort of an arbitrarily shaped conductor that we're going to play around with. The very first rule is one that you probably already have seen, which is that the electric field is zero inside of a conductor. So basically everywhere inside of this piece of metal, the electric field has to be zero. We know that's true because we thought about the fact that if there weren't an electric field of zero, if there was an electric field, then all the charges that live inside that conductor would move around until the electric field became zero. That means we've got an electric field of zero everywhere inside of this little trapezoid. There's a couple of immediate consequences that come from this. The first one is that means that the change in the electric potential has to be equal to zero for any 2 points inside of the conductor. So I can pick this point and this point, this point and this point. Any 2 points in here, including points on the boundary, have to have no change in potential. That doesn't mean the potential has to be zero. It just means that the change in potential between 2 points has to be zero. So whatever the potential is, say, here at the corner, that's the value of the potential everywhere across the piece of metal. There's another consequence to this, which is that if all the points in here have the same potential, then by definition, the entire surface of the metal, including the outer surface, is what we know is an equipotential. We've drawn some equipotential maps, some equipotential lines before. And one thing that we know is that the electric field should be perpendicular to those equipotential lines. Well, here I have an equipotential surface, and I know the electric field is zero inside. Zero is perpendicular to anything. But this also then is going to tell me that the electric field outside has to be perpendicular to my surface. So I can go draw some electric field vectors at the surface here to tell me that the electric field is always going to be perpendicular to the surface. Now that's only true locally, right at the surface. If I go over here, there's no surface next to me to be perpendicular to, so this rule doesn't apply there. But now I know that the electric field is going to be perpendicular to the surface of the conductor, and this is on the outside of the conductor. And these two rules follow directly from what we already said is true about the electric field being zero everywhere inside the piece of metal. So we're going to add a couple of extra rules here, and I'm not going to prove these, but there's good rationale for them based only on what we've done so far. One of them is that all of the charge that lives on the metal is either going to be neutral, is going to be electrons and protons all paired up nicely, not doing anything interesting, or that charge is going to live on the surface of the metal. There won't be any free charges just living in the middle like that. Instead, any charges that live on this piece of metal will do so out here on the edges. Something like this. So I'll add this as another rule here, which is the charges live on the surface. And then one last rule that I'm going to give you is that depending on the shape of this piece of metal, I could get different amounts of charge in different places. And it turns out that when you have sort of wide regions like this or big curved regions, that you tend to get lower charge densities and therefore lower electric fields. Whereas when you have corners like show up in these different places, especially down at this corner, you actually get that the charge density ends up being bigger in these little corner regions, and therefore the electric field ends up being bigger. So I probably need to draw a few more electric field vectors there and to make sure that it's a bigger field, so maybe something like that. And then I'll add my last rule here, which again is that the charge density, and because of that, the external electric field, the electric field right outside of the piece of metal, are largest near corners. All right, now we have a whole set of rules for electric conductors that we can use anytime we encounter ideal conductors in our studies.